Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
So it's my pleasure today to introduce Alan Fekete to you all. I think Alan actually knows everybody in the room, so in some sense he needs no introduction at all. He's from the University of Sydney, and he has a long history of being involved with and doing research in transaction processing. Over the last several years, he's sort of focused his efforts on exploiting, in some ways, snapshot isolation in multiple ways, and has done some very nice work, including the Sigmod Best Paper Award in, what was it, 2008, on how to use the versions that you have from snapshot isolation to provide serializable transactions as well. So Alan continues to work in this area, and the talk today is on performance aspects of that sort of work. So I'm really happy to welcome Alan here. He's been a longtime friend and colleague, and I'm sure the talk will be very interesting. Thanks.
Thanks very much, Dave. So I should just set the context. Today's talk is purely an experimental talk. So we don't have any new algorithms. We don't have any new proposals. What we have is some measurements. And so the idea is just to look at some of the algorithms that have been published, including the one of our own that Dave mentioned, but also a number of others, and see what happens when you actually run them. So just a quick marketing. I noticed I'm on sabbatical at the moment at Berkeley, and I noticed that company talks always start with "we are hiring," so we're a university, so we can't say that, but at least we can sort of advertise that we exist and that there is database research at the University of Sydney, and should you have any interns or whatever who at any stage are looking to come out for a period, that would be a wonderful thing.
Notice the sunshine in that picture.
Yes, so
for those of you who don't recognize it anymore.
So this work is in the context of OLTP style activities. So we're looking at programs where there is a significant amount of modification going on of the data, not just analytic workloads, and the standard ACID properties that people want. Particularly here, focus on isolated and the different things that isolated might mean. I guess I wasn't sure about the audience. With this audience, I think I can skip the concept of what concurrency control is. Quickly back to the serializability, which is sort of the academic approach to capturing what isolated might mean. And so there's this nice definition that one covers in a database course, that you have Phil in particular has spent years developing people's intuitions about this. The key things here are that the importance of serializability to me is fundamentally the fact that it gives you this preservation of integrity constraints even when the database doesn't know about the integrity constraints. So it's easy enough to have a database that will maintain a declared integrity constraint, but if there's an integrity constraint which is complicated to express, the nice thing about serializability is that that integrity constraint will be maintained even without the platform knowing about it, provided you write each program to be sensible on its own. So it turns a global problem into a local problem at each program. And there's the standard theory that you can do this by looking for the absence of cycles in a graph showing the conflicts. So that's the academic situation. The reality is, of course, that a lot of the programs out there don't run with serializability, as You know, I don't know, does anybody know if there is any platform at all for which the default is serializable? I'm not aware of one. All the ones I am aware of, you know, give you something like read committed as the default, and a lot of people are running their transactions without realizing that they need to do something. So there's a lot of weaker isolation out there.
According to the Spanner paper, they want to serialize.
Right, okay. So that will be,
I don't know what they really do.
yes, yes. So anyway, so weak isolation is something that's a practical reality, and so, you know, given the people in this audience, I don't need, I think, to say too much about snapshot isolation. It's been successful in practice. You know, Oracle have, I think, done everybody a substantial disservice by confusing the terminology. So snapshot isolation is an isolation level which is not serializable, but is a very valuable isolation level in many ways. It has plenty of good properties. You know, you don't get the typical anomalies. You don't block readers, so that's very helpful for a lot of applications. One of the things I should say about snapshot isolation that I've found in teaching, many students, when you explain serializability, the intuition that they build up is actually snapshot rather than serializability. Students, I have found, the way they develop a sense of what isolated ought to mean is that when you have concurrent transactions, they should be isolated from each other, that neither should see the other. And of course, that's what snapshot isolation gives you, rather than there is a serial ordering of them, which is the academic definition. So clearly, snapshot isolation hit a very sweet spot in the space.
What you're calling the academic definition is actually developed at IBM.
Yeah, it's the one that is taught academically. So thanks to Phil for pointing out that it's actually the industry definition, but not all of the industry at the present time, at least. And it's the one that is covered in the textbooks. So maybe I should say the textbook definition. So, snapshot isolation does not, in fact, give you the textbook property of serializability in every situation. You can get this standard, you can get this anomaly of right skew, where two transactions don't see each other and violate integrity constraints because each of them is modifying different data. So it doesn't happen in most of the benchmarks that are out there, but you can design programs that make it work.
The reason why it doesn't happen in the benchmarks is because Oracle was involved in negotiating what the benchmarks were.
So,
Is that really true, though?
Oracle wasn't going to participate in TPCC because they were asked to run serializable, and they could only support true serializable with table-level blocks. And they negotiated, and then the TPC council thought it was very important to have Oracle in the process. And so the idea was you don't have to support serializability, you have to run serializable for the benchmark.
So that, I mean, if that's true, then TPCC somehow would violate serializability running SI.
No, it's run serializable even though you use SI.
yeah, so the TPCC benchmark gives serializable executions on SI.
So the claim is that there was some earlier definition of the benchmark for which that wasn't true.
I don't know which one was the first one, but after TPCC insisted on serializable executions, Oracle was threaten not to participate unless they can do it without table double lock.
I wasn't there. People here are much closer to the action. I'll defer to them. So I hope I don't need to sort of walk through the example. This is one I like because it's one where one can actually sort of get a sense of how important it could be to have integrity constraints be protected. So this is one where you're running a hospital and you want an integrity constraint which says for every day there is at least one doctor on duty. And by having programs concurrently take doctors off duty, what you can end up with is that the final state is one in which nobody is on duty. And so that seems a very real world impact from the loss of textbook serializability from running snapshot isolation. One of the most important things, though, again, which I find is not intuitive. I mean, for most low levels of isolation, like read committed, the normal way people think about it is to say, look at your program and decide whether your program needs serializability or whether your program could run read committed. Snapshot isolation is not like that. You can't look at the program and see whether it has some feature that needs snapshot isolation. It's not a property of each program. It's a property of the collection of programs as a whole. It's purely from interactions. And it's even more complicated. You can have 3 programs which which give serializable executions under snapshot isolation. You introduce a new program, and then you need to alter what's being done in one of the previous set of programs because of the new program. So in order to reason about this, we need some form of serializability theory that deals with multiple versions. There have been a number out there. The papers I have worked on typically use the version of the theory from Raz, which is a slightly simplified from the most general definitions, but they're easy to use and easy to write down as a paper, in a paper. In particular, for everything like snapshot isolation, you have a version order that's given to you. The most general definitions, the ones Phil, I know, worked on a lot, involve quantifying over version orders in the theory. And in our case, we just take the commit order as the version order because that's what snapshot isolation does. And so we operate that way. So you can draw your conflict graphs for multi-version histories, and you get the standard result that if there are no cycles in the graph, that tells you that your execution is serializable. The important thing to notice is that it's the read to write conflicts which are particularly critical in snapshot isolation. They're the ones where you have a transaction which reads a version and does not see the effect of another transaction which is writing the same item but is producing a later version than the one that the first transaction reads. And those already Atul Ajja's paper now almost 13 years ago sort of established the importance of these conflicts for weaker levels of isolation. So anyway, using that, we draw a serialization graph and we distinguish the edges which are from read to write conflict and between transactions which are actually concurrent with one another. So those edges are the ones that we're going to pay particular attention to in the diagrams. I'm going to generally show them as a dashed edge. That's what's called the anti-dependency. So the theory which I developed, extending stuff that Atul Ajja had done, but a theory for snapshot isolation is that the crucial thing to look for is a situation where you have two of these vulnerable edges in a row in a cycle. So it's not just that you have a cycle, but you have a cycle with two of these anti-dependencies between concurrent transactions successively. And the theorem, so this is work I did with Pat and Betty O'Neill in 2005, is that that's the critical thing to look for when understanding whether you've got serializable executions or not in a snapshot isolation system. So, following on from that, Dave already mentioned work principally by Michael Carl, who was at that stage a PhD student of ours at Sydney, has since graduated and is currently working, I believe, for Wired Tiger. Proposed slightly changing the concurrency control algorithm to be very similar to snapshot isolation, have the same nice properties of snapshot isolation, but guarantee that the executions were serializable according to the textbook definition. The basic idea is very simple. It is, if we can track when you get these vulnerable edges, when you have a read-to-write dependency between concurrent transactions, and you look for cases where you have two of those in a row. And whenever you have two of those in a row, you abort, that should ensure that you have serializable executions, because serializable executions would have to have two of those, non-serializable executions would have to have two of those in a row, and you abort one of the transactions, that throws it away. But it should be a lot cheaper than traditional optimistic concurrency control, where you essentially prevent all the conflicts from happening. So you should have to do a lot less. So Michael proposed mechanisms. Oh, yes?
Sorry to take you back, but could you, so this rule that takes, if this happens, then it's not serializable. Could you show how this, like on this example of the bound, of the on duty? Oh, this is exactly what happens, that this thing is
sure.
violated.
So, with this situation here, what you have is, so transaction 1 is reading both these records and writing this one. Transaction 2 is reading both these records and writing this one. So what we have is that we have so transaction 1 has an anti-dependency to transaction 2, because transaction 1 has read the Smith row. It did not see the change made by transaction 2, so transaction 2 produces a version which transaction 1 did not see. So that is an edge from T1 to T2 of the read before a write. If we look at the Jones row, that's a case where transaction 2 reads it and does not see this one's write. So that gives you a dashed edge. So what we have is a cycle of two dashed edges, one after the other, and they're the whole cycle. There are no others. Okay? So that's what's happening here.
So your theory proves that this is a necessary and sufficient condition for serializability?
Okay, so you have to be here. No, so what we show is only one direction. If you have if you do not have that structure, then you get serializability. Obviously, sorry, let me briefly. If you have that structure in a cycle, then you have a failure of conflict serializability. Now, it is still possible that even if it's not conflict serializable, it is serializable in, say, view serializable sense because of, some of those writes being blind writes or whatever. So, conflict serializable is actually an approximation to view serializability. But, for our point, our goal is to ensure serializable executions. It's okay if we occasionally abort unnecessarily. I mean, there's a performance issue and you have to worry about how much that is. Okay, so essentially Michael's approach, I mean, the basic idea is look for these two edges in a row and abort. When you see that, pragmatically how Michael suggested to do that was in every transaction you have two flags. One flag which says there is some edge coming in. There is a flag which indicates if there's an edge going out. And every time you see one of these read to write dependencies, you set the out flag in the first transaction and the in flag in the second transaction. And whenever you see a transaction with both its flags set, you abort it. It's not quite that simple because sometimes you discover that both the flags are set in a transaction which has in fact already committed. Basically that transaction's committed and you're now doing another dependency from another transaction. So at the time you discover it, then you have to abort a different transaction, but you still abort one of the transactions in the cycle and you still protect things. How does Michael propose to actually detect these situations? So the simplest case is somebody did a write, you're now reading the item, but you do not see their write because you're operating on a snapshot. That case is particularly easy to detect because when you do the read, the algorithm for finding the correct version for you to return goes down the list of versions, sees this one, sees that its timestamp is greater than what you're trying to read and skips over it. So the moment you skip over it, you know here is a case where there is an edge that's been produced. The case where you do a read and then later somebody comes along and produces a version, but from a concurrent transaction, Michael proposes to do that by sticking in the lock manager a special lock mode to record that the read happened. And when this write happens, it's not blocked by that lock, but it knows that there is an edge, and so it goes and puts the appropriate flags into the transactions. And Michael, one of the things is you actually have to keep these locks around longer than transaction commit time. You've got to keep them for another, basically until every transaction which had started after this transaction has finished. So you have to keep them a little bit longer, but they don't block anything, so they're just sitting there in the lock table. So Michael's approach does sometimes abort unnecessarily. It's a conservative approximation. It, for example, doesn't check whether you've got two edges in a cycle. As soon as it sees two edges, it aborts. And sometimes that means that you're aborting things which will never show up in a cycle. Michael implemented this into InnoDB, so the back end for MySQL. It was very, very simple. He ended up adding 230 lines of code to the storage manager, most of which were simply to track these flags and keep them around and then garbage collect them as necessary. So we have an implementation of Michael's algorithm that he did. Then in 2011, another proposal was published for serializable snapshot isolation. So this was by Steve Revelak, a student of Pat and Betty O'Neill from UMass Boston. And what they proposed was to say, let's try to get rid of these false positives, these unnecessary aborts. And what they propose, they call PSSI, for precise serializable snapshot isolation. And essentially, it is a very old algorithm, serialization graph testing, right? They keep the serialization graph and check it for cycles, and if there's a cycle, they abort. Okay, so that was their proposal. They did an evaluation in that, so they implemented that into InnoDB. And for their paper, they did an evaluation where they compared it to an algorithm which they and we refer to as ESSI. So it's basically a similar idea. It's the same idea as Michael Carl's. And I mean, they use it as a proxy for Michael's algorithm. Namely, you just look for two edges and don't bother with checking the full cycle. But their implementation is actually very different in the code, and we'll discuss that. So they had this, and Michael Carl had his, all done in InnoDB. So we thought this would be an interesting place to actually try and do an experimental discussion and see how these different algorithms play out. Let's look at, there are basically several different implementation design decisions in these systems. So the first is, in some sense, goes to the heart of what Michael was trying to do. So Michael tried to make his algorithm be very lightweight, not intrusive on the InnoDB code. And so Michael tracks things very lightly, basically has two flags for each transaction. The alternative is you keep this global serialization graph, which is a big data structure that everybody shares. Then there is the one which is in some sense, the algorithmic rather than the implementation issue. Are you trying to, or how accurate are you going to be in deciding when to abort something? You know, the more approximate, the less close you are to exact, the more unnecessary aborts, and there could well be a performance impact from that. And then the other one is, again, an implementation issue. When do you do the checking? And so I'll go through each of these in turn. So, as I said, Michael's algorithm, you have two flags for each transaction. One which says, do you have a dependency in? One which says, do you have a dependency out? So the benefit of this is that you really have very local information. Each transaction just keeps its own threads. It has to, when there's a conflict, you have to update one other transaction's flags, but there isn't a global structure. The downside is that those flags, firstly, they're just Boolean. You know, is there an edge in? So if you've spotted an edge in and then the transaction at the other end aborts, you don't have any way of knowing that that came from a particular transaction and cleaning it out. You leave the flag there, and that can cause you to abort unnecessarily. PSSI, of course, tracks the full dependency graph, and Revelak's implementation that he used as a proxy for Michael's, ESSI, also keeps that whole dependency graph and tracks everything at the level of which edge there is, which transaction you are depending on, or which transaction there's an edge out to. The downside is that you have this huge data structure that everybody's sharing, but I mean, for PSSI, you can be incredibly precise, but even for ESSI, you're much more accurate than just with a Boolean flag of was there an edge. Then, do you look for a whole cycle, or do you just look for 2 edges in a row? So here, PSSI goes for cycle detection, whereas both SSI and Revelax proxy, ESSI, do it just when there are 2 edges. And obviously, if you don't bother checking if your edges are in a cycle, that allows false positives and unnecessary aborts will occur. And then the other one, again an implementation issue, Michael Carl's code basically does this on each operation. When you do a read, you see if you're skipping over a version, and if so, you set the flags at that point. When you do a write, you see if there is a conflicting but not blocking lock indicating a previous read, and if so, you set the flags. And every time you go in and set flags, you check if somebody has 2 flags set, and if so, you abort. So Michael's algorithm is doing work on every operation. PSSI and Revelax proxy for Michael's algorithm, ESSI, both do no work at all during read and write. No work other than what is happening anyway. They do everything at commit time. So when the transaction goes to commit, you go into the lock table and see what other transactions had set locks, and you build the extra edges into your conflict graph at that point, and you do a cycle detection and you abort. So here we have the potential advantage that with Michael's, that you might detect things earlier. On the other hand, that also means that you're going into sort of the work frequently, and if you have many operations, it may well end up being more overhead than just doing it once at commit time, where you could get it all in a single hit. So at least on the surface, it isn't clear which of these will perform better. There are definite advantages and disadvantages each way, and complicated trade-offs. So we thought there would be an interesting experimental evaluation to compare them. So that's what we did. So maybe we should start with what we had. So we basically got the code from Steve Revelac that they used in their system. That was in a relatively recent version of MySQL with InnoDB at the back. Michael Carl's system had been implemented in a somewhat older version of InnoDB. I mean, Michael Carl's work was in sort of 2008, whereas Revelax's 2011. So we've got several years of progress. So we took Michael's code, and taking advantage of the fact that we had Michael around to consult, took it into the same release that Revelac had used. So we had a common code base with Revelac's implementations and adaptation of Michael Carl's. So we had Michael's SSI, and Michael had also implemented pure SI as a comparison. So we took his port of that also. So we had that. So this is work that was done in collaboration between people at Sydney University and Seoul National. At Seoul National, they have plenty of nice equipment, and so we took great advantage of that. So we've got a 24-core machine. So that's, they're not 6 corers, they're 6 cores. I think that's probably spell checker at work. 4 dies. the structure is core private L1 and L2 cache and die L3 cache. We followed both Michael Carl's experiments and Revelak's experiments, and we set it up to do something which is almost group commit. It's not proper group commit because MySQL doesn't have proper group commit, but you set it so that the log gets flushed only periodically, so it stops the log flushing becoming the bottleneck, which otherwise it would tend to be very, very early in these experiments.
Does InnoDB support snapshot isolation of this looking?
Okay, so InnoDB itself is a complicated system. It is a multi-version system. Its serializable level, however, is two-phase locking based. So it doesn't use the versions if you're running with serializable. The versions are used for its concept of read committed, which is not the usual read committed. It's some very bizarre, different thing. So Michael implemented snapshot isolation using the versions that were there for their read committed and the code to read a particular version. So it's snapshot isolation is not there out of the box. So what we have is we have Michael's code for snapshot isolation, but it's very minimal change. I mean, the nice thing about InnoDB, the reason Michael used it, is it already had both the versions and a lock manager. Unlike Postgres, which had the versions but no lock manager at the time, and other systems which had a lock manager and no versions, InnoDB gave both the pieces that he needed. So as I said, his whole code doing both snapshot serializable SI and SI itself was 230 lines of code. And then the clients are running on a separate machine which is tossing requests at this. So we use a micro benchmark. It's basically 3 tables, the transactions, read one of the tables and write a different one. And because they have all the ways you get cycles coming up. Here's one experiment. So remember, our goal was to see how these different algorithms compare. And sometimes, the middle, the third one here is Michael Carl's. Then the Revelak proxy for it is here, and the cycle detecting one is at the end. And the first bar is always just snapshot isolation as a baseline. So, sometimes the Revelak ones do better, sometimes Michael Carl's do better. There doesn't seem to be much in it. The difference from snapshot isolation is not that great, though it does seem that these are suffering. And so probably you might say, okay, so the conclusion of the comparison is it depends, but not much in it. Perhaps the most interesting thing is that in fact sometimes even Revelak's proxy for Michael's algorithm does better than precise. But really, I think if you were looking at this, you would say, really, it's not important enough to worry about. So, one other thing that we did was, so the first experiment I showed you was a case where it's 75% read-only transactions and 25% updating transactions. If we vary the proportion of read-only transactions to updating transactions, we do see significant difference, but again, what you're seeing is not much difference in the performance between the algorithms at any particular workload. Though with a very high rate of read-only transactions, we do see that snapshot isolation is pulling well ahead, and you're then paying more for serializability. Whereas with sort of the cases where you have a more limited amount of read-only, the costs are in the range of sort of 10-15%, which is what people, both Revelac and Michael Carl's papers report.
For 100%, there's no rights, right?
That's correct.
So SI has like a 20% or maybe even more than the
Yes.
SSI with flags, so it's just flags, right?
Yes. Okay, so things are getting interesting. And indeed, the most interesting figure is what happens if...
Things are coming into focus.
Yes. So if instead... Previously, I sort of showed you a graph up to here. Let's have a look at allowing the MPL to keep going. Multi-programming level, the number of concurrent clients that are throwing requests at the database. So this is going back to the workload which is 75% read-only, 25% updaters, which is sort of the one we sort of regard as in some sense, the most natural one to look at. And this is what we found. And basically, the rest of my talk will be not talking about the differences between these three algorithms, but in fact, this much more noticeable issue, which is that the performance of all of these algorithms collapsed catastrophically as the multi-programming level went up, as you try and get concurrency into the system. Okay, so so people expect to reach a bottleneck and plateau, but a collapse is a sign of some worry in the engineering of the system, I would have said. Yes?
How big were these transactions? How many reads and how many writes?
So these transactions are, I think, the ones which did 20 writes and 100 reads each, of pretty small records. We did experiments where we made the transactions bigger by an order of magnitude. I mean, it changes the numbers, but not the phenomenon of the collapse.
100 reads and 20 writes, those are relatively big transactions already.
Yeah, but I mean, not that big. Yeah. So, but we're seeing a distinct collapse, and that's really what this talk is about. That collapse and our attempts to understand that collapse and explore it. So if we look at the runtimes of the transactions, what we see is that the collapse goes along with transactions taking much, much longer. So snapshot isolation transactions at the read-only transactions at snapshot don't go too badly, though they do get a bit larger. The updating transactions get a lot longer, but with the serializable versions, they really slow down, and you're seeing a very substantial penalty showing up in the runtime there. We also looked at abort rates, and while at MPL 30 you're beginning to get aborts, the performance collapse is already at 20, and you're not getting a lot of aborts at MPL 20. So it's not from lots of aborts and retries. It really is that the transactions are running much longer. Some profiling. So this one is set up so that each algorithm, we show what's happening as the MPL increases. So this is snapshot isolation. This is Revelac's, Michael's, and the precise version for Revelac's. And what we're seeing is the huge amount of time in holding the mutex. So
Is there a mutex on what? On the log table?
it's a mutex on the entire database kernel.
Wow.
InODB
Wow.
has a mutex on the database kernel. Well, it did. There is a release candidate. It's not yet, I think, the official current version of InnoDB. But so InnoDB is moving towards a situation where it's refactored to try to divide the mutex. But at this stage, it is a kernel mutex, single kernel mutex.
Every operation in the InnoDB runtime, updating InnoDB internal data structures holds one shared mutex.
Yes.
So it's a 24-core machine. It's actually bottleneck on.
Yes. It's not every. It's only if you have to modify the structures. But yes, this is basically being the problem. So essentially, you're taking these mutexes to avoid. It's the latch to avoid modification of shared data structures. What's even worse is this is what's happening with a read-only workload. Okay, so there is no logical contention here. You're still getting, however, if you're running with these algorithms, you are still getting the various locks. You're recording things. They're not blocking anybody, but you are recording them. Or you're doing a check at commit time of this graph. It will not have any edges in it, but you still have to go and do the check, and we're seeing this performance collapse. Pure read-only workload is just... So snapshot isolation is managing to keep going, but the other ones are all collapsing appallingly. Let's also, I'm sorry for the blurring of this. This seemed to be something when I took stuff out, so I'll interpret this figure so you can see. These are the same sort of graphs with MPL from 1 to 30. The bars are in the same order. This is what happens when we run on 4 of the cores. So the platform has the capacity to essentially make some of the cores invisible. You can say use only certain cores. So if you run on 4 cores, you get this. If you run on 12 of the cores, you get the collapse already. And fundamentally, running on 24 cores, you do worse than if there was only 1 core there. That's the basic story.
Is the NUMA effect magnifying the performance?
So we did experiment with doing it whether the cores were on the same die or otherwise. There are some differences, but it's not the dominant thing. I mean, so whether you're you're sharing the level 3 cache or not, it's not the big effect. There's a small effect in that for the PSSI and ESSI, sometimes you can work so that if you're on a single die, the whole serialization graph fits into the cache on that die. So that can give you a bit of advantage, but it's not a strong effect. The collapse is not from that. So, here so this is one where we've actually plotted out. So this is 1 core to 24 cores, and you see that at MPL 30, your performance is as bad on 24 cores as it is on 1 core. And already at 12 cores, you've got a fairly substantial collapse. 4 cores you do pretty well on. And it's interesting, the earlier papers of both Michael Carls and Revelax were typically looking on machines with 2 cores or thereabouts, but 24 cores is really causing problems.
Is the reason that in the serializable algorithms, you need to take the database mutex to mark the dependencies?
So, yes, so all of these algorithms are taking that database mutex in one place or another, and I'll now drill into where those places are. This just again shows the experiments on different numbers of cores, and at MPL 10 you don't get dramatic increase in the amount of time you spend in the mutex. But if you look at MPL30, you're getting this huge effect. Even once you get 12 cores, you're getting lots and lots of time spent with the kernel mutex. So let's have a look at where the mutex gets taken and why. So with Michael Carl's code, so Michael Carl went to a lot of trouble to have it so that each transaction has transaction local flags, but you still end up scanning the list of transactions to find the transactions, to check the other transactions. And that is a place where you end up getting the kernel mutex. So you do that on every read and write. You don't do much inside that, so you take it only for a short time, but you do it often. With Revelac's algorithm, you do nothing during the transactions running, but when you go into commit, you take the kernel mutex and you then have this huge thing which updates the global dependency graph and runs a cycle detection over it. So, yeah, both of them have problems. What we do see is that the ones which operate on the global dependency graph tend to collapse earlier and more extreme. But Michael Carl still collapses, even though he went to all the work of trying to have stuff with sort of transaction local flags, just because of the problem of finding the transaction in the transaction table. So, okay, so the problem, as been alluded to, the problem is the fact that you have a kernel mutex which everybody was using to protect everything. And that's where the collapse came from. Just as an interesting thing, we decided also to profile the snapshot, serializable snapshot isolation. This came about after we'd done the previous work. Then Postgres introduced their implementation, which was based on Michael Carl's original ideas, but they implemented it in Postgres, involved not just as a research prototype as ours were, but so this is now the production code of Postgres. Postgres is now using Michael Carl's algorithm with some further refinements. So this was a VLDB industrial paper last year. So they have structures where they don't have a single global mutex for the kernel. They have stuff sort of separated out, and they have sort of a separate latching structure for the little different little bits of the shared data. So in a sense, it's similar to Michael Carl's algorithm. However, it's a bit more accurate. Firstly, they don't just set Boolean flags, they actually track which transaction is at the other end. So you get fewer cases of a dangling flag left by a transaction that aborted. They also have some additional optimizations, including some for analytics, which don't matter for this. So we also took their code and measured that. For this, we actually used the TPC C++ benchmark, which is one that Michael Carl invented. So it's basically TPC C, and you add one more transaction to the mix so that you actually have a situation where snapshot isolation wouldn't work correctly. And so that was run. This is done on a 32-core machine. And what we see here is there is still a performance drop-off, but it happens much, much later and it's not nearly as bad. So here, so this is MPL 128, you're down by a third from the peak at about MPL 32, but you haven't collapsed catastrophically. Though it's still the case that with high MPL, you are definitely paying for serializability compared to snapshot isolation, which PostgreSQL still has available. So if you ask for repeatable read, you get snapshot there. And if you ask for serializable, you get serializable snapshot. So this shows that, serializable snapshot isolation is not something sort of intrinsic to the algorithm that you have this performance collapse. It comes very much from the implementation details and how you share the mutexes. But even here, with some careful work, and the Postgres people did measure it on machines with some numbers of cores, as you get to 32 cores and higher multiprogramming levels, you are really hurting still in performance. I guess the conclusion I would give is that, and here you guys are way ahead of us, is the great importance of thinking about the implementation details and particularly the latching that goes on in order to get decent performance on the sort of high-end servers that are coming. And so, really thinking about what is shared and how you protect what's shared become vital. We agree with all the previous papers that these serializable algorithms don't have much penalty compared to snapshot isolation when there's one core or two cores, but at the moment the algorithms are still not taking good advantage of lots of cores. And the work, though, what we were suggesting was not so much algorithmic rethinking of the concurrency control, but implementation rethinking to avoid contention over latches. And that's where I am, and I guess I will hear more about the way you've sort of gone all around this and managed to do stuff with both concurrency control changes and algorithmic and implementation ones.
Thank you very
much. I presume that some of these papers, past papers on serializable snapshot isolation, have had something to say about the performance drop-off from snapshot isolation, perhaps simulating it or doing it in some more controlled setting. All concurrency control algorithms ultimately become a bottleneck under sufficiently high contention. Can you give us a sense of what would be expected if that were the only effect?
Okay, so
it's nice to actually see it on those graphs.
Okay, yes. So I don't have it. Actually, let me just go in. I may have some of Michael's slides among the hidden stuff. So let me just see if I've got some of those. Okay, so anyway, maybe let me go back to summarize. What Michael found in his experiments was there were lots of situations where the concurrency control wasn't the bottleneck. So most of the cases he did, snapshot isolation and his serializable snapshot isolation, the performance was very close. However, he could tune the situation so it became a bottleneck, and then you can start getting substantial drop-offs. Most of the time, that wasn't where he found it.
Well, the question is how much the divergence is. I mean, you're going to get some drop-off even for snapshot isolation. I mean, if you get a high enough conflict level. So it's
yeah, but so
the question is what's the spread between
Yeah,
Anyways,
so
take it.
Michael got graphs many of his graphs basically, you had SI, SSI, and 2PL essentially on the same curve. But he was able also to get graphs where you had SI, SSI, and 2PL with something like 30 to 50% there by choosing the weight of the transactions appropriately, putting the right delays in them.
I don't know. We have an implementation of Rakesh Agrawal's PhD thesis simulation of concurrency control algorithms that we used for an earlier study, you may recall.
Yes.
It'd be interesting to get some kind of apples to apples comparison of these things just purely based on the concurrency control algorithm's behavior. Because there's so many moving parts to try to actually do it any other way is going to be really, really difficult, and it's worth knowing.
Yes. So, I guess, yeah. So the first thing, of course, is just trying to understand what environment will it be that will make the concurrency control the bottleneck rather than all the other things.
All the transaction benchmarks are designed to have that effect, and so
that wasn't what. Well, I guess the first thing is, you have to do something to make sure that the log, the disk writes of the log don't become the bottleneck. So you have to have something like group commit turn on. So otherwise, I think that's the one that hits you first. All of these are done with everything fitting into main memory. So that takes that out. Yeah.
I'm not expecting an answer. It's sort of a rhetorical question, but I think it might be, if you're interested in pursuing this line of understanding performance, I think that would be a useful.
Yeah. So, I mean, what we found here, so one of the experiments I didn't show you was we did the one where we really sort of crunched down onto a hotspot to try to get contention in the concurrency control as the issue. But basically, it doesn't turn out to be that much. So what we found there was that, when you make it a hotspot, all three of the SSIs are dropping off. They're all dropping off far more than SI is. So they are all collapsing. And even... Yep.
When you have right conflicts. You have more, like naturally, just by design, by definition,
Sure.
you have more conflicts. So I can come up with any workload, like construct artificial workload, and I can cause like as much conflicts and aborts and slowdown of the output. So I can even in theory come with analytical model, which will cause whatever amount of aborts I want and whatever slowdown.
Yeah, but so, I mean, there's the difference between SI and the others. But then within the SSI variants, there's also how they go. So, how many false positives you get from just looking for 2 as against from being more precise, how many false positives you get from not cleaning up when an edge from an aborted transaction. So you do.
You're saying more than that. I think my takeaway from this is those sort of differences, the differences at the concurrency control level are small. This is really sensitive to how you build the concurrency control mechanism and what mutexes you use to protect the data structures within the concurrency control mechanism itself.
Yeah.
If it's latch-free, maybe it does a lot better than if it isn't.
Yeah, but I mean, Phil's question is, suppose you got away from all of that and really just looked at the concurrency control.
It's kind of a weird presentation. I mean, you had this rather lengthy build-up about serializable
Yes.
snapshot isolation, and in the end, you told us about the way database kernels behave badly,
Yes.
which is actually the choice of concurrency control algorithm is quite irrelevant.
Yes.
Yeah.
Yes.
You know, I mean, so
Well,
which
I mean,
is-
it's
which
not
is it-
completely
what is
irrelevant
the talk
because,
about,
I mean,
know?
you still have the fact that snapshot isolation doesn't have the collapse nearly as badly as all the serializable variants. So,
Pretty interesting that they're that crude, but
yes.
anyway.
So I mean, I think there is still a takeaway which says, you know, the price of getting serializability, which, you know, Michael and we've argued was manageable. It was like 10% at the most compared to snapshot under most conditions. Turns out not to be true with enough cores, with the sorts of implementations that we had. Now, one could maybe, and we're trying to find better implementations which don't have these issues. And the question is, can you get it to close to what snapshot isolation has under those conditions?
So the takeaway that I get from this is that what matters, what really shows up here is how efficiently you can maintain the data structures that you have to maintain, and how efficiently you can do it under high concurrency, right?
Yes.
And those effects are now so big that you can't really see the difference between the various algorithms.
Yes.
Right?
Yes. And I mean, the thing is that for snapshot isolation, pure snapshot isolation, when you read, you don't have to do any modification of the internal state. And so that's fast. And it doesn't cause all these problems. Whereas all of these things, when you do a read, you have to record the fact. And that you're paying for.
So if you want to go this route, you really need essentially a log manager that can handle very high levels
Yes.
of concurrency.
Yes, you need a smarter lock manager that can do this. And you have to think about the whole system in terms of what you're doing at each stage of the checks. I mean, Michael had tried to do this in designing it so that the flags were transaction local. But in the implementation, he just didn't check all the other bits. And
With a big mutex, there isn't that
Yes.
much you can do.
Yes.
Your host.
yes.
Well, thank you very much, Alan.
Okay.
Really good.